Hello, everyone, and welcome to our event this morning. My name is Mike Weitzman. I'm Senior Editor of Robotics for the Robot Report, and I'll be your moderator today. And today we're continuing our ongoing educational series into the technologies that support autonomous mobile robots. And today we're going to dive into vision and AI localization. But before I get started, I have a few housekeeping items to cover. This session will be recorded, and the recording will be available after the session for viewing at therobotreport.com. If you're rewatching a session, please use the same login information that you used today to watch this session on demand. The slides for this session can be found in your screen's Attendee Resources window, so you can download a copy to your computer now. You can personalize your experience by adjusting the webinar's window size and moving the widgets around on the ON24 control panel. At the end of the presentation, a question and answer period will be held. So please use the designated Q&A widget to submit your questions throughout the session. Finally, if you experience any technical difficulties, try refreshing your browser window first. This typically solves 99% of the technical issues. Or you can always access our webinar producer by clicking on the Help widget. We've got you covered with all of the latest news, information, and education about robotics at our portfolio of sites that include the Robot Report, Collaborative Robotics Trends, and our newest publication, Automated Warehouse. So before we get started with our session today, I'd like to thank our sponsor for today's content. That's Argo Robotics. And you're going to learn more about Argo Robotics in the session today. This webinar explores how vision and AI are enhancing autonomous mobile robots in real-world applications. Our speakers today are Alon Zengut, VP of Delivery at Argo Robotics, Matthew Goa, Head of Sales, and Jack Miller, Senior Applications Engineer. So welcome, Alon, Jack, and Matthew. The stage is yours.
Thank you. So this is Matthew speaking here, and I would like to, kick things off with a quick question for all of you guys, robotics engineer. If you could solve one major challenge with your current localization solution or navigation system in general, what would that be? Well, some of you might say improving commissioning time, others might focus on boosting performance in dynamic environments, or maybe some guys would just reduce the map maintenance to a minimum. You can think about those challenges. You can feel free to share them in the chat. But the reason I'm asking this question is because, well, as you might have guessed, today we will be exploring the vision-based perception and how it can unleash the full potential of mobile robotics. So let's dive in with our crew. I will start with the introduction, and then Alon and Jack will walk you through all of the more technical details of our solution. Today, the presentation will go as follows. I will start with a quick introduction for you guys. Then Alon and Jack will go through the reliable operations everywhere, the quick and easy site commissioning, and also demonstrate how our perception engine lays down the foundation layers for AI into the robotics. And then we'll wrap things up with some Q&A. So, Argo Robotics, I think it's a nice start to start with our mission. And our mission, as you can see it on the screen, is to enable mass adoption of intelligent automation with AI. To do that, what we do is that we empower machines and mobile robots to be more accurate with affordable and reliable human-level perception so they can see, understand, and adapt to the real-world environment. Who we are at Argo Robotics to fulfill that mission, we are basically a bit more than 30 employees today. Most of them are experts in computer vision and sensor fusion. And as we speak, our product, the perception engine, has been already deployed in hundreds of machines, and we have thousands of units already ordered. The company has been funded in 2018, and as you can see, most of the staff has experience in computer vision and AI and IT in general. So what we do, it's basically a product which is called the perception engine. The perception engine, is a full stack solution that will enable localization and perception for your mobile robots. It is tightly coupled with a low-cost camera reference design, and it will allow the mobile robots to actually answer three questions, which are, where am I, where can I move, and what are my surroundings? This stack is designed specifically for wheeled machine, and the learning engine, which is powering the solution, it has been trained with thousands and thousands of kilometers of data already. So the value proposition of the perception engine, before we actually dive into it, it's really a unique learning vision system, which leverages visual SLAM, but also AI and sensor fusion to enable three main benefits. The first one is an easy and fast deployment for any kind of mobile robots because it is 100% infrastructure free, and it comes with a powerful API and a very user-friendly UI, which makes it usable by anyone in your customer's team. The second thing is that it will dramatically streamline the commissioning and maintenance of those robots. The reason for that is because, first, the map creation is 100% automated. You don't need to edit, fine-tune, clean up the map. It's fully automated. But more than that, the system is continuously learning and updating the map, so you don't have to actually maintain it. If there are any changes in your warehouse or in your facility, the system will update accordingly. And last but not least, because it can operate in very dynamic environment, indoor, outdoor, but also because it comes with a very, very accurate, with a very high level of accuracy and reliability, it opens up to very wide range of applications. So that is what the perception engine is bringing to the table. And now I will let Alon and Jack, walking you through the details of the solution.
Thanks, Matthew. All right, so in the next few slides, we'll go through some of the significant challenges that plague mobile robot applications, particularly regarding navigation and localization. As we do, we'll highlight a few case studies where we encounter and address such challenges with our proprietary VSLAM and sensory fusion algorithms. At a high level, we'll go through how production environments are ever changing, the unique challenges associated with indoor and outdoor operations, and the effects repetitive environments have on mobile robots. So as we talk through dynamic environments, I'd like to highlight one of our partners, WheelMe. I think dynamic and adaptive are the perfect words to describe WheelMe's product line. And as such, they need a localization system that shares those values. If you haven't seen their product, each wheel is an omnidirectional mobile robot, as you can see on the left. And they mount several of these wheel bots on existing carts, trailers, and other dunnage, as you can see on the right, in a variety of configurations so that anything can become a mobile robot. It's pretty cool. It's worth noting that all of the floor stage product in the image on the right is work in progress staging and is constantly moving throughout the facility day by day, hour by hour. I'll get into the video here that shows the vehicle operating in this environment. And anyone who has spent time designing, deploying, or even buying traditional LiDAR-based mobile robots has surely encountered the not enough static features problem that this highlights. So as I play the video here, you'll see several environments as they're changing features is a very common aspect of their applications. So you can see there's a product on either sides of the warehouse in that facility. All sorts of different configurations for their mobile robots and their platforms. Very dynamic, very adaptive, needs a lot of support from a localization perspective in order to accommodate some of these very challenging environments. So it is worth noting that Argo wasn't the only system that WheelMe had investigated for localization. In fact, the Visual SLAM wasn't even the only technology, but we were the winning solution. These are some of the reasons why WheelMe believes in a partnership with Argo. No need for remapping. We have an experienced team working full-time with perception and localization. Some of their end customers had very direct quotes saying that with Argo, no more drunk driving behavior was present in their robots. The robot localization seems way more accurate, and Argo seems like a real game changer for the product performance. And with that, I'll hand it over to Alon to discuss indoor and outdoor use cases.
Thank you very much, Jack. Hi, guys. My name is Alon. I walk through the next one, which is the indoor and outdoor operation, which has become more and more demand for today's mobile robots. This environment characteristics and use case, the environment is changed dramatically. The surface can be from gravel to pavement to grass, all the way to the snow, actually. And lighting conditions and uneven surfaces are definitely challenging the robots to navigate accurately within the environment. As you can see in the picture, Kappa Robotics is also one of Argo partners and customers, which based in Denmark, is one of the best examples in the market for those use cases. As the motto goes, multiple applications, they've taken it to the whole new level, all the way from inspection use cases, smart cities, and of course, indoor and outdoor intralogistics. They were pioneers by really understanding the challenges in navigating indoor and outdoor, and they chose right away vision-based navigation to be able to operate seamlessly within those environments. And of course, Argo Perception Engine provide with a full 6 degrees of freedom localization, stands for X, Y, Z, and pitch, roll, and yaw. One of the challenges mobile robots are facing with this scenario is wheel slippages, where the geometry readings can be very messy. That's one of the challenges we face it, and we mainly face it when we saw some even wet floors kind of stuff. And how we face it is by implementing a multimodality, by using different sensors and fuse those ones, such as the camera, IMU, gyroscope, magnetometer, besides the wheel odometry in the camera, of course. And that way we constantly evaluate where the robot is and can compare between the camera readings and the different IMUs to really evaluate where we are. Additional challenges we faced was also accurate docking station, even picking station. And this way we implement a high precision mode that can extract relative position to Argo markers with a millimeter scale accuracy. In the pictures, you can see a different example. So Capra Robotics use Argo Perception Engine all the way from a cart dragging on the left to a ROEC assembly and configuration where they're using indoor and outdoor configuration. Niels was the former CEO and one of the founders of MIR, Mobile Industry Robotics, and he's the guy that actually created Kappa Robotics. And what he said is Argo is continuing to develop a game-changing navigation technology, emphasize that traditional localization sensor, they can do either indoor or outdoor, but not both. And Argo Robotics, by combining those capabilities into a low-cost, compact, and robust system, was their key aspect and strategy how they can succeed in the market. In the next video, you can see a very nice example of how this product is utilized and deployed in the market. So you can see the Kappa robots navigating outdoors, so between different sites, carrying load. So you can see it can go all the way from the outdoor environment into the indoor environment seamlessly, continue its mission, approaching picking station, which requires a very accurate navigation skills. And that's implemented with a single monocular camera facing front and additional IMUs for the Argo perception engine. They had a very extreme different use case, was working with a wagon in a slaughter warehouse. You can see the floor is completely wet. The site itself has a very challenging environment, and that's extreme, right? And the perception engine really makes the robot work seamlessly over there. Let's stop over here and facing the next challenge, and let's handing over back to you, Jack.
Thanks, Alon. So the next challenge that all mobile robots encounter at some point are repetitive environments. So you may have seen we recently announced a partnership with Onboard Robotics, and their use case takes repetitive environments to a whole new level. In many mobile robot applications, there's typically 1, 2, maybe 3 areas that are classified as repetitive or featureless. Think of a long stretch of path along a featureless wall or down a long aisle of racking on both sides. Well, for Onward, that is the environment that they live in day by day. Their facilities are large grids of shelving for order picking operations, environments that all look identical to a 2-dimensional LiDAR, which often leads to a tunnel vision effect where most mobile robots lose localization or have pose jumps quite easily. Now, a traditional 2D LiDAR approach would be to add infrastructure to the shelving that would provide a certain uniqueness to recognize and guide off of. But many of the aisles in these facilities, however, are quite narrow and do not have the option of adding infrastructure. For Argo, we're able to have a 3-dimensional perspective of our environment. This enables us to use many different features in our localization algorithms. And there's no doubt that these environments are objectively challenging. We've had to overcome a few of our own challenges to support these environments. But in each of these challenges that we've overcome, it has iteratively improved our product in the long run and has prevented our partner from tackling these challenges on their own. Some of the reasons why they chose Argo is because of the flexible and adaptive perception is critical to business success for their applications. And we're able to support with our own team dedicated to localization, while the Onward team is able to focus on their value proposition from their product perspectives. Okay, so we just talked about the challenges of localization and navigation in deployed sites, but what about mapping a site for a new deployment? The image here shows a typical 2D LiDAR scan of a facility. Now you may be able to look at this image and think, okay, there's some aisles, intersections, maybe some production equipment, some racking. Probably safe to assume that all of the white space is free space, open for maneuverability. But that's the best most people and most robots can recognize from this image alone. What you would then miss is that there's a guardrail towards the north that LiDAR would either miss or only see the legs. There are 3D obstacles, such as tables and overhanging shelves, that are also missed or only seen as legs. There's open dock doors and other doorways that may be mistaken for available maneuvering space. Empty storage space may appear as available aisle space. Racking with product outside the 2D scan plane only shows legs of shelving. And some areas that appear occupied during the mapping process are actually just temporarily blocked by pedestrians, forklifts, and pallets at the time of mapping. So all of this missing information needs to be identified. It's typically by a skilled technician or engineer and manually altered in the map to have a functioning system, right? Oftentimes these are forbidden zones or free zones, right? And map cleanup in order to make this system to be something recognizable for a robot's operation. So our claim is that AI and 3D computer vision can ultimately automate this map cleanup process. And so we'll get into the foundations of that claim in some of our current features and features in development coming up here with Alon.
Thank you, Jack. So let's talk about site commissioning, or how we're learning a new site with Argo Perception Engine. So a few facts about it. The site exploration or the mapping phase need to be done once. So there's no need to remap or readapt the map if the facility has been changed. This is done automatically over time with continuously updates to the map, which reduce a lot of time and hiccups for the system. The map doesn't need any post-process or manual cleanup, as Jack mentioned. It's automatically post-processed and ready to use within minutes. Then the map can be shared with the entire fleet. And there's maybe one of the top priority facts is there's no need to stop the operation of the facility. So sometimes with traditional 2D LiDARs and other technology, if there is a pallet in the middle of the floor or some forks that may be obstruct, they need to be cleaned up or need to be removed. With Argo Perception Engine, you can map the site without interrupt the day-to-day operation, saves a lot of runtime to the facility. And of course, it goes for both indoor and outdoor. Let me try to maybe demonstrate a little bit how it seems in one of the test sites we're having next to the Argo offices. So this is typical logistics centers when you can have those racks outside, and you can see the environment is different changing. So there's pallets here, and there's some typical racks on the other sides. And maybe to start with, a first calibration needs to be done. And when I mean calibration, we just need to measure where the camera is positioning in related to the robot. And that's done once when you come to the site. It's very easy with the intuitive UI, as you can see. You can just create a new site, create a new map, and just turn the robot in place where the robot automatically detects itself, how it positions in relation to the robot. And then you can go straight away, get accurate position and mapping without going into too much complicated calibration processes, such as for systems today. Once you're done with the calibration, all you need to do is travel with the robot and see the site, because we're a camera, we need to see the site in different perspective. And the minimum is just 2 perspectives. So going down the aisle with 1 perspective, going back and forth, the second perspective, and there you go. Once you finish with this one and cover the aisles, you have a ready-to-use map, ready-to-use mission, and you can start operate within this warehouse. Maybe another example that we use sometimes for forklift tracking application is the ease of use of a blueprint or a CAD drawing of the site. And this is one of the examples when a forklift just traveled the warehouse once, map the sites. Then we use our UI to align the blueprint of the facility to the Argo coordinate frame. And there you go. A few minutes after, you can see the live position of a Mandarin forklift or autonomous forklift on the blueprint or the CAD of the site itself. Makes it very intuitive and very easy to start work with. The next chapter will concentrate on the foundation and AI, and that leads me straight away to Jack.
Thanks, Alon. So the simple fact is that precise localization and computer vision are foundational to the use of AI in mobile robots. With our learning-based VSLAM, we're already blazing the trail of AI perception capabilities in mobile robots. And we'll get into some of the features that we've been developing in this regard as well.
Thanks, Jack. So back to mapping. We already show you how we map with our monocular vision and create a nice data structure of a site. But now when you utilize deep learning algorithm and training mechanism, you can map a free space site using the single monocular only. So what you can see in the video on the right part is a monocular monochrome camera that actually detects the surface. So it has a surface classification algorithm And with that, with the accurate position and the surface classification, it will create a full global free space map of the site. What is nicer to add to this one is the ability to detect and classify objects within the image. So we spoke about free space by utilizing the surface, but what about these objects? Using a camera-based technology, you can see objects such as pallet and loading gates and storage areas, detect those ones in the images, and then with accurate position, overlay them on the map, resulting with one quick scanning with a ready-to-go map with a lot of annotation and information ready to go to plan and deploy your mission in no time.
All right, and so now that brings us into one of our other features that is using generative AI. This is the Argo Insight Engine. It's a feature we've been developing recently to use large language models and visual-based data to provide operational insights to end users of our product. So as I play the video here, you can see the image on the left shows the layout of the facility, while the right side provides a query field along with corresponding image and response descriptions for a location that matches the query. We'll get the video started here now. So what if you could ask your forklift insights about your operation? What are some of the things that would be important to you? Now you can see here we're typing in a query into the Insight engine. And once the query is submitted, all the little yellow triangles on the facility layout to the left show the location and orientation of the Argo system where a matching query event occurred. So in this particular case, we're looking at unsafely stacked objects, right? And you can see the image that corresponds with that location, as well as a description below that describes what is actually happening in the image. Right, so now we're talking about PPE equipment for operational personnel. So it's all a matter of what is important to you, what is the visual data that you would like to unlock, right? And then as the course of these language models develop and continually iterate, it's only going to become more and more robust and more precise for whatever your actual needs are. All right. So thank you. That's all we had from a presentation perspective. I think if we want to open it up to Q&A.
Yeah, well, thank you guys for pulling this together. That was very interesting. And as was just mentioned, if you have a question, you can use your Q&A widget in your console to enter that question now. We've got a few already queued here, but we will get to some of those questions now while you guys are busy doing that. So let's see. Let me, and I don't know who wants to answer these, so I'll just ask the question. You guys can decide who's the best resource to pull this together and answer for this. So one of the questions that came in is that, let's see, if I have a camera on my robot already, can you work with that existing camera, or do you need specific cameras, or what's your compatibility?
Sure. So it's a good question. I can take that one. So our system, we use, I'll say, off-the-shelf reference hardware, right? But we do have specific configurations of the camera modules with additional sensors built in. And we do have a calibration process that allows us to really utilize those sensors appropriately and have high confidence in the data that we're getting back from them. So unfortunately, at this time, I don't think it's as simple as utilizing a camera on your existing system. I think it's more about incorporating the hardware we recommend and the calibrated sensors that we recommend so that we can integrate ourselves into your system holistically.
Interesting. Well, here's another related question then on that same topic that also came through. How long does it take to integrate your solution to a new platform then?
Sure. So I will step in and take answer for this one. Good question. Typical integration with new platforms, roughly for a few days, we usually set up the first prototype. That means evaluation kit we have in Argo. We just need to set up Ethernet connection with odometry. And usually it goes through a phase of 3 weeks till month of evaluation. Once that's done and we fine tune the use case, then it's only a matter of a few months to get it real deployment. But first integration and first setup, it's only a few days.
Interesting. Well, here's maybe a somewhat related question. I know you had a couple of examples of outside robotics. So this person's asking, what about outside? I can see you make it for lawnmower. I can see you also make it for robot lawnmowers. How precise are these under trees or near the house, for example?
Sure. So outside applications are one of those beautiful applications I personally like. They're very extreme challenges and it's very dependent on the environment, right? All the way from small lawnmowers to man-driven big mowers machines, and also to a survey vehicles that we are working with. The accuracy will be very dependent on the environment and the use case, but I can say that typically accuracy will be sub 10 centimeters in terms of precision for those use cases. Of course, it depends on the environment itself, but this is the complementary technology for RTK outdoor, right? As you have open sky, you have good RTK reception, and you don't see many features. But once you go in under trees, next to buildings, you don't have RTK, but you have a lot of features for the vision system, and this is where we step in. So definitely, I would say sub 10 centimeters will be the accuracy level, and definitely this will be the complementary technology for utilizing outdoor application.
Well, it was good. You proactively answered another question that someone had about the accuracy and repeatability. So good job combining two into one. What would be then the minimum amount of light required for the robot to operate? Assuming, I mean, you're using vision for a lot of your sensors. Talk a little bit about the conditions.
Yeah, so vision system needs to see. It's a human level of perception. So think about it as a human being, right? If we are in a completely dark pitch black room, we cannot see and we cannot operate, same as humans. The minimal lighting condition on the spec is around 100 lux, but we can measure and operate even in 50 lux, which is a relatively shared dark environment. And I think that's one of the strengths. We did implement our own mechanism from auto gain control for the camera, and we are controlling the exposure. So even if you have an open source or different camera exposure models that design to get the best camera and picture exposure, we designed our exposure mechanism to be optimized to our algorithms. So we don't care sometimes if it's going to be overexposure in some areas in the camera, as well as we see the interest and the region of interest area exposure with the right exposure, so we can extract feature out of it. So I'll say 50 to 100 lux is going to be the minimal lighting condition operating.
Great. Well, you're doing a good job. You answered another sort of related question about the performance at night. So good on for that one. What would be the typical specification for the computer on board or the compute that you need to run the vision system, or talk a little bit about the specifications on the infra for the machine?
That's a brilliant question, and I think once beginning days we started with lawnmowers, we were aiming to end user machines, and when you mean end user machines, you need to get it cost effective, right? Most of the small machines and robots, they can run on a 6-core, 8-core CPU. We use a rock chip, for example. That can be very, very low on compute, but that depends on the features, of course. If we need localization, low speed, the compute requirements be very low and can be very competitive. But then if you go to big machines, need higher speeds, then sometimes you go to a bigger compute. And also feature-wise, if you want to use deep learning, classification, object classification, and cognition, then we usually need some GPUs. Most of our customers are currently using Jaguar platform, which is commercial off the shelf, with only the cost of 150 euros, around 200 euros, with the Rockchip CPU. But we also now working very tightly with the Orin NVIDIA family to support multiple features, and Qualcomm and others as well.
Interesting. I thought there were a couple of map questions. I was trying to find the first one, but there's definitely one up here that oh yeah. So sort of two mapping questions. I'll ask the first one. How are the maps stored and accessed on the system?
Sure, Jack, would you want to step in? I don't want to steal all the questions.
Sure. So that's a good question. I assume this question is in relation to the actual localization map that we build out as the system runs. So it's stored in a series of database files, and there's a map folder directory that stores all that information. And locally on the compute, it's stored in the main SSD or NVMe storage device, just so that there's long-term memory of it. So as Alon had already mentioned, it's a continuously building map, right? Continuously updating, but it is stored locally on each device, on each robot, and can be shared to other robots throughout the fleet.
And a related map question then is, how's your performance for a really large map? And maybe I'll sort of add some color to it. Give us an example of what's a large map that you've or facility or outdoors, or give us an example of some of the largest maps that you've worked with.
Sure. So I can at least give one or two, and Alon, if you want to add on to any, feel free to jump in. So we're doing some really interesting forklift tracking, testing, and evaluations in facilities as large as 400,000 square feet. In those types of facilities, some of the specific repeatability data that I've seen has been down in the 2 to 5 centimeter accuracy levels. And that's repeatability. So starting, logging a point of interest in one corner of the warehouse, driving through all new areas of the facility, coming back around to that main point of interest, and recapturing the positional data for that location. And we're finding between 2 to 5 centimeters of repeatability there, which is quite impressive, especially how large a forklift is. And then, I think a frame of reference, I think a Post-it note is somewhere around 4 or 5 centimeters. So you think about that's the level of precision that we're seeing for a forklift in a 400,000 square foot facility. It gets pretty big. It gets pretty impressive there.
I like the Post-it metaphor. Everybody can comprehend, exactly how big that might be, for a large facility. That's a great metaphor. Now, there's a couple questions here about open source and support here. So let me ask the first question came in. And by the way, I'll remind everybody to ask a question, use the Q&A widget in your user interface to ask us a question. Got some good questions going here. So when integrating to a platform, what do you support specifically? ROS 1, ROS 2, both?
That's a good one, Mike, and thank you for that, for asking this one. Sure, we're fully compatible with ROS 1 and ROS 2 API, but our core capabilities SDKs is C++ based, right? Most of our companies uses ROS 2 maybe for preliminary integration to evaluate as it's easy to start with, but then we find it most useful just use our SDK C++ API for fully product deployed integration. So ROS is supported, but when you want to go deploy, you just use the C++ API, best way to go.
Well, and then another question came in, how is your solution different from the competition, including open source? So, I mean, I don't know if you already answered that, but if you want to add any other color around that.
Sure. The real answer, it just work. It just work. It work beautiful. It's deploying the units, and it's work everywhere. But I think the magic is like how we implement it, right? You ask about big sizes and map, people know, use big size, they imagine, you save a lot of images. It must be very load, big maps, database, how to transfer, how to share, how to load. But the magic is how much image you need to save. What is the frequency you update those ones? How you implement multimodality with different sensors in order to utilize and maximize your technology. So there's a lot of magics and experience inside, and I think the reason we are deploying multiple and variety of applications, indoor, outdoor, fast vehicles, slow vehicles, accurate one, gives the real answer that it's actually work and ready for deploy for any different application.
I think I'd like to add on to that a little bit as well, just specifically regarding open source and our comparison to it. A lot of our partners start with open source navigation systems, right? And I think WheelMe is a great example where, whether it's Cartographer or RViz, there's different open source systems that they actually start off with. They find that they're just not meeting the needs of their what are classically known as edge cases, right? And I like to say that our system is kind of built on those edge cases for those edge cases that many of the open source platforms just can't handle. A really specific example, one of my first few weeks. So a little bit of background on me. I come from AutoGuide and near 5 years in LiDAR-based robotics as an application engineer. And some of my first few weeks with Argo, I had the opportunity to observe some of the projects and challenges that Argo and WheelMe had tackled together. And in one of those situations, I remember walking through the facility and just looking around, and some of the videos showcased it today, where there's just floor stack product everywhere that's constantly moving throughout the day. And it was a particularly challenging use case that they had originally tried open source platforms with, and it just couldn't handle it. And my response, seeing it, I couldn't believe that that was the type of facility that we were even operating in. And with the Argo system, I was shocked at how successful they were in such a dynamic and changing environment. So yeah, I think there's a lot of examples of that where we talked about dynamic and repetitive environments specifically that are significantly challenging to both open source and closed source systems, right? And the Argo system is best in class from what I've seen.
Great. Well, we've got a few more questions here before we wrap things up. Here's one. Talk to me about how you manage sensor calibration, because you talked a little bit earlier in the session, using sensor calibrated sensors is important to understanding what you're seeing in the scene.
Yeah, so I think calibration is kind of the magic word in vision system. A really good calibration brings really good results. There's two different aspects of calibration. The first one will be the intrinsics. So how to calibrate the camera itself, the camera module. This is done in the factory with Argo algorithms to accurately calibrate the focus and the distance of the camera with its lens. So that's once. Second calibration will be the mechanical calibration of the camera placements in relation to the robot body. So the XYZ and the portfolio of the actual installation. I've kind of touched it in the webinar before, but we have an on-site calibration procedure. We just turn in place maneuver. We estimate and measure all the sensor noise and calibrate exactly where the camera position without the use of external tools or unique kits. That's make us very easy to use and very accurate to operate.
Interesting. Yeah, that is pretty a nice feature and capability during the deployment. Here's maybe a related question. It's a map question, and this individual is saying they missed some concept of the localization in the video. And they're asking, do you have a master mapping machine that initializes the scene? Maybe that's what you just described, and update the low-cost moving robot or forklift applications that updates it. So it just sort of goes on, and maybe I can ask a little bit more clarifying here, but it's a question about how you're handling the map saving and sharing with other AMRs as well.
Sure. So I can take an initial stab at the question, and Alon, if you want to chime in as well, feel free. So the best I understand the question is kind of regarding, do you have a master machine that does the mapping, and how are we sharing it across the fleet?
I think that's it. Yeah.
So there is a robot, there is a machine that will go through and do the mapping. We don't provide it per se. It's part of our customers, right? They are deploying 30 robots at a facility. One of the robots they choose to use for mapping, they map out the facility. Once the map has been created, we can then share that map to each and every one of those robots. At that point, each robot has its own map stored locally. So to your question, there's no master server, right? That's overseeing the whole facility. Each robot perceives and understands independently, but because of all robots are operating in the same environment, in theory, the map is identical between all the robots. And if at any point in time you need to swap out a robot, hardware issue or whatever, it's a matter of copying over a map, any one of the maps, onto that new robot, onto the new storage device, and starting up. So I hope that answered that question, but Alon, I don't know if you had any more to add.
Well, I think you did. So, yeah, go ahead.
No, I said you answered accurately. The whole just using the same database with a global coordinate frame for the same site.
That's the concept of a map. Yeah. Right.
Yeah.
So we got two questions left here in the queue. I'll take this first one, which is regarding safety. Is your system certified, or how would you describe safety certification of the system?
Sure. So I'll take a stab at it, and Alon jump in. But yeah, so our system is not safety rated. In fact, some of what I've been seeing and we've been seeing in the industry is transitioning from safety rated devices to safety related devices, and so we've actually started to see some interesting activity regarding how using multiple modalities and multiple sensors can actually have a better, have a more of an impact or a better impact in the safety related activities of a robot. We currently don't go through any sort of safety certification in that regard. If you're talking about obstacle, human detection, stopping, those sort of things, right? But it is quite an interesting time and an interesting shift that we're starting to see on going from the traditional safety rated devices, a single safety rated yellow LiDAR, to multiple modalities, either vision plus radar plus whatever else, 3D LiDAR, and some of those sensing equipment that traditionally was not rated safety is now starting to actually take hold on safety related activities. So I think there's some other blogs and webinars on that, I'm sure, but our device is not safety rated.
Interesting. All right, so here's one last question then before I let you guys go and we wrap things up, and maybe it's a good way to sort of finish this up. What's the usual process for a test or a proof of concept? So if someone's interested in deploying the system and seeing how it works. How does that roll out for you guys? Who wants to take that?
Sure.
Sure.
I'll take this one.
Yeah, go ahead, Alon. You got it.
So POCs and evaluation, I think, is one of those well-structured process that we go through with our customers, because a customer want to see it works within its robot, with its environment, right? So we basically start discussing about the needs and the requirements. Then we talk about how and where to integrate the perception engine into the robot. Then usually our customers define the test plans, whether they want to work with this side or these sides, and we have a structural test plan and test approach, how to evaluate the system. Whether you test it with a dynamic environment and change the scene, whether you test it very, very repetitive. And we use sometimes external ground truth system to evaluate the performance. Then we usually sum it up with a performance evaluation report, demonstrates how well we perform in their side with their platform, with their robots. And I think the fun part is to see when they have those areas when they know the current system will fail and they try to fail us as well. And then all of a sudden, the LiDAR position jump off or lose position, but they see the Argo position is quite solid. I think that's most the part where the customer are convinced the technology can be used for in the use case.
Great. Well, thanks, Alon. And hey, I want to thank Argo Robotics for sponsoring the session. I want to thank all you gentlemen for your time in presenting the solution to us today. 2 reminders: if you want to download the presentation, do that now from the console. But you can also learn more by going to Argo Robotics, all one word, .ai. And learn more about their solutions. And again, this session will be available for replay at therobotreport.com. So you can always come back to it if you miss something. So that's going to do it. I want to thank our producer, Lindsay Harvey, and the rest of the WTWH webinar team for their hard work in pulling this together. My name is Mike Oitzman. Thanks again, everyone, for attending.